Motion. 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 Everything with which you come into contact is in motion. This aircraft is in motion through the air and over the ground. That it is in motion is obvious to the observer on the ground. However, to the occupants inside the aircraft, their forward motion is less obvious. Relying on the sensations of the forces acting upon their bodies, the passengers can feel the aircraft rise and fall with changing air currents. They are alternately lifted out of, then pushed down into their seats. As you sit in a room watching this program, you are moving through space as the Earth both circles the Sun and rotates on its axis. As you move through space, there are forces at work that do not make themselves immediately obvious. As long as the motion of the Earth remains constant, you feel no sensation of movement and are probably only vaguely aware of the force of gravity holding you to the surface of the Earth. Any sudden change in the motion of the Earth through space would produce instant and very dramatic effects. The other forces acting upon objects on the Earth's surface would become immediately obvious. In this program titled Newton's Laws of Motion, you will learn about these forces and their effects upon all matter. All matter in the universe has mass. Mass is a measure of the quantity of matter in a body. The terms mass and weight are often interchanged. Keep in mind, however, that an object on the surface of the Earth has both mass and weight. An object in space has mass, but no weight. Weight is the product of the gravitational pull of the Earth upon nearby objects. All objects have an attractive force for other objects. The gravitational or attractive force between two objects varies directly with the mass of the objects and inversely as the square of the distance between them. Two large objects relatively close together will have a stronger gravitational force between them than two smaller objects the same distance from each other. The gravitational force between any two objects decreases as those two objects are moved farther apart. If the distance between the two objects is doubled, the gravitational force is decreased to 1/4 of the original force. The English physicist Sir Isaac Newton described the relationship between the mass of a body in motion and the forces which are acting upon it. This relationship is explained by three natural laws that have been dubbed Newton's laws of motion. Newton's first law states that a body at rest tends to remain at rest, and a body in motion tends to remain in uniform motion in a straight line until acted upon by an outside force. The property of matter which this law describes is called inertia. Inertia of a body is directly proportional to its mass. The greater the mass, the greater the inertia. Only a slight amount of force is required to set this tennis ball in motion or to change its direction or stop it once it's in motion. However, a much greater force is required to overcome the inertia which tends to keep the bowling ball at rest. And once the bowling ball has been set in motion, it takes a considerable amount of force to alter its path or to stop it. The bowling ball has a much greater mass or quantity of matter than the tennis ball. The inertia of this space vehicle would tend to keep it moving in a straight line. Were it not for the gravitational pull of the Earth, the vehicle would leave Earth orbit and go streaking off into outer space. The force of gravity between the Earth and the satellite forces the vehicle to follow a curved path. You feel the effects of inertia on your body as you sit in a car which starts, speeds up, then brakes to a stop. These effects can be illustrated visibly by suspending a weight from a convenient point on the car and watching its reaction to the effects of inertia. As the car begins to move, the occupants and our suspended weight appear to be forced backwards. Actually, the weight wants to stay at the starting point, but is forced to move forward with the car. As long as the car continues to accelerate, the weight will tend to stay in one place, giving the appearance of moving backward in relation to the motion of the car. As the car reaches cruising speed and ceases to accelerate, the weight hangs straight up and down, moving at the same speed as the car. As long as the speed of the car remains steady, the weight will continue to move with it. Watch what happens when the driver applies the brakes. The effects of inertia again become visible as the weight appears to move forward. Inertia tends to keep the weight in motion at a uniform speed, but as the car decelerates or loses speed, it's continually moving slower than the weight. The weight is trying to maintain its speed and is decelerating at a slower rate than the car. Newton's first law states that a body in motion will continue in uniform motion in a straight line until acted upon by an outside force. One of the outside forces we must consider is friction. Friction of the wheel bearings and of the tires with the ground. Without the continuous force of the engine to overcome friction, the car will coast to a stop on level ground. Newton's second law of motion deals with acceleration, or the rate of change of velocity of a body in motion. Newton's second law states that the acceleration produced in a mass by a given force is directly proportional to the force and inversely proportional to the mass of the body. Let's consider the two parts of Newton's second law separately. Acceleration, or the rate of change of velocity, is directly proportional to the force applied. A bowling ball may be set in motion by a relatively small amount of force. However, a greater force will produce a greater acceleration of the bowling ball. The rate of change in velocity from zero to the velocity at the time the ball is released is illustrated here. The ball in the lower half of the picture covers a much greater distance in the same time period as the ball in the upper half of the picture. Force and acceleration are shown to be in direct proportion to each other. The second part of Newton's second law states that acceleration is inversely proportional to the mass of the body. In other words, the same force applied to objects of different mass will cause a greater amount of acceleration in the body with the least mass. The same force applied to this tennis ball and to the bowling ball will produce markedly different rates of acceleration in each. Acceleration is measured in feet per second in the English system, or centimeters per second in the metric system. An object that accelerates at 10 feet per second, or 10 feet per second squared, is increasing its velocity 10 feet per second for every second it travels. The same amount of force that produced the 10 foot per second squared rate of acceleration on the car will produce a much slower rate of acceleration in this truck with a much greater mass than the car. The force of gravity produces a uniform rate of acceleration on a freely falling body. The rate of acceleration caused by gravity is 32.17 feet per second squared. The same rate of acceleration is produced on all freely falling bodies, regardless of size or weight. That explains why two objects of much different size and weight, when dropped from the same height, will both reach the ground at the same time. The acceleration caused by the force of gravity is equal on both objects because the force causing the acceleration varies with the mass or weight of the object. The lighter object has much less force acting upon it than does the heavier object. A 2-ounce object has a force of only 2 ounces acting upon it, while a 1-pound force would be acting on the object weighing 1 pound. The acceleration produced in an object can be calculated by using the formula F equals W times A divided by G, where F equals the force required to accelerate a body, W is the weight of the body, A is the acceleration produced in the body, and G is the acceleration produced by gravity, which is 32.17 feet per second squared. A force of 1,000 pounds is exerted on a 4,000-pound car. What is the rate of acceleration? Applying some basic algebra, we find the answer to be 8 feet per second squared. A 1,000-pound force applied to a 4,000-pound automobile will cause the vehicle to accelerate at a rate of 8 feet per second for every second that the force continues to operate. In 10 seconds, the automobile would be traveling at a speed of 80 feet per second, or about 55 miles per hour. Newton's third law of motion states that for every action, there is an equal and opposite reaction. The kick you feel against your shoulder when you fire a rifle is an illustration of Newton's third law. As the powder charge explodes, the expanding gases confined in the barrel of the rifle exert a force on the bullet, sending it toward the muzzle. The same force is being exerted against the cartridge from which the bullet was fired. Since the cartridge is physically held in the breech of the rifle, the force is transmitted to the rifle butt. You feel this force against your shoulder. Newton's third law is also illustrated by the internal combustion engine. A cylinder filled with volatile gases receives an ignition spark. The expanding gases exert a force in all directions in the cylinder. In one end of the cylinder is a movable piston. The force exerted on the cylinder head is also exerted on the piston head. The piston moves downward in the cylinder. That downward motion is transmitted to the crankshaft by the piston rod and converted into rotary motion, which turns the propeller of an aircraft. While we are considering the laws of motion, it will be helpful to differentiate between two terms which are often used interchangeably: speed and velocity. Speed is simply a rate of motion and is measured as a distance per unit of time. In this case, the car travels at 25 miles per hour. Velocity is the distance an object travels in a unit of time and in a particular direction. An airplane in a climb may be traveling at a speed of 100 miles per hour, but it may also have a vertical velocity of 700 feet per minute. Vectors or vector quantities are expressions of velocity. Vectors must have both magnitude and direction. Vector quantities added together will produce a resultant vector quantity. A simple method of adding vector quantities is to lay them out on a graph. Use the divisions of the graph to represent magnitude and use directional arrows. The direction in which the arrows point may be related to a starting point, clockwise around that point. Simply draw the arrows to the proper length and in the proper direction and add them by placing the arrows nose to tail, one after the other. Then, draw an arrow from the starting point to the end of the last arrow. This is the resultant vector quantity. The length of this arrow is the resultant magnitude, and the direction from the starting point to its end is the resultant direction. This method is used widely in plotting vectors for navigation problems on a chart. The direction the aircraft must fly is plotted in relation to a compass rose. Direction is related to degrees clockwise from the north reference on the compass rose. Magnitude is drawn to scale using degrees of longitude and latitude to represent miles per hour or knots. An aircraft flies at a speed of 100 miles per hour on a course of 045 degrees. Then turns to a course of 090 degrees and increases speed to 120 miles per hour. Then the aircraft turns south to a course of 180 and reduces speed to 90 miles per hour. What is the resultant vector? Establish a starting point. Draw a line from that point parallel to the 045-degree line on the compass rose. Mark a point on the line representing 100 miles per hour. Let 1 degree of latitude equal 10 miles per hour. The length of the first vector would then be equal to 10 degrees of latitude. From that point, draw another line parallel to the 090 line on the compass rose. Again, mark the length of the line, this time using 12 degrees of latitude to represent 120 miles per hour. Draw the last line parallel to the 180 line on the compass rose and use 9 degrees of latitude to represent 90 miles per hour. Connect the starting point with the end of the last line. Determine the direction by relating the line to the compass rose. The length of the line in degrees of latitude will be the resultant speed. The resultant vector quantity is 097 degrees 30 minutes at 190 miles per hour. You'll recall that Newton's first law of motion stated that a body in motion will continue in uniform motion in a straight line until acted upon by an outside force. Two of these outside forces become apparent when we begin to consider circular motion. A spacecraft in orbit about the Earth follows a circular path. The force that would pull the spacecraft to Earth is balanced by a force acting in an equal and opposite direction. The force that tends to pull the craft away from the Earth is called centrifugal force. It's balanced by an equal and opposite force called centripetal force. Swing a weight on the end of a string. You can feel centrifugal force trying to pull the weight from your hand. You exert an equal and opposite force on the string to keep the weight following its circular path. You are providing the centripetal force. If you let go of the string, centrifugal and centripetal force no longer are acting on the weight. Inertia tends to keep the ball moving in a straight line from the point at which the weight was released. Grinding wheels are rated for operation up to a maximum speed. The adhesive materials which hold the particles of the wheel together are not strong enough to overcome the centrifugal force at speeds above the maximum rated speed. Exceeding the rated speed of the wheel is extremely dangerous because the wheel could disintegrate, causing damage or severe injury. Let's review what we've learned about the laws of motion. Newton's first law of motion states that a body at rest tends to remain at rest, and a body in motion tends to remain in uniform motion in a straight line until acted upon by an outside force. Newton's second law states that the acceleration produced in a mass is directly proportional to the force applied and inversely proportional to the mass of the body. Acceleration is the change in velocity of an object per unit of time and is measured in feet per second squared or centimeters per second squared. The force of gravity produces a uniform rate of acceleration on a body of 32.17 feet per second squared, regardless of the size or mass of the body. The relationship of weight or mass of an object to the force applied to produce acceleration is expressed by the formula force is equal to weight times the rate of acceleration divided by the acceleration produced by gravity, 32.17 feet per second squared. Newton's third law of motion states that for every action there is an equal and opposite reaction. The kick you feel against your shoulder when you fire a rifle is an illustration of Newton's third law. Speed of motion is the measure of distance traveled by a body per unit of time. Velocity is the speed a body travels in a given direction. Vector quantities are measurements of velocity. Vectors may be added by drawing them to a specific length and giving them a direction. The sum of the vectors equals the resultant vector quantity. Two additional forces are introduced when we consider circular motion. They are centrifugal force and centripetal force. Centrifugal force tends to pull an object moving in a circle away from the center of the circle. Centripetal force keeps the weight moving in a circular path. When both forces cease to operate, such as when the string breaks or is released, inertia tends to keep the object moving in a straight line. From the moment an aircraft leaves the assembly line, the forces of nature are attempting literally to destroy the aircraft.